Welcome everyone. My name is Ed Hartnett, and I would like to acknowledge my collaborator Kyle Gerheiser, who works with me at NOAA at the EMC. Before we start, I would like to bring up this lovely example of software in which an integer overflow caused the loss of an over $500 million launch of the ESA Ariane 5 Flight 501. I think that one of the important lessons to draw from this software bug is that the system which caused the bug was a system that was only used when on the ground, and it was never tested what would happen if you just left it running. And as the launch happened, it just kept running, and then it overflowed and caused the rocket to explode. And I think this is a great example of how software in a system can be quite a bit more interconnected than we think. We divide the software up into different modules and programs and such, and we think that it's very separate. But a bug anywhere in your large, complicated software system can cause disaster. So what are we talking about today? We're going to demonstrate how we use GitHub Actions to perform continuous integration on some science codes. And thank you all for attending the Improving Scientific Software Conference, which I have found very interesting so far. I'm going to draw examples from 3 different projects, which are all out there on the GitHub. The Parallel IO library are some C and Fortran libraries that do netcdf IO on high-performance systems. The NCEP libs are a set of libraries which are developed and supported by NOAA and are part of the UFS system, as well as other important operational codes. And the Community Codec Repository, a new project which introduces some new compression filters for netcdf. All of these projects use GitHub Actions to test with continuous integration. I'm going to talk about it in 4 sections here. We're going to talk about unit testing in CI. Then I'll explain how we can use GitHub Actions to do it, what the output looks like, and then I'll point you at the repositories of the example projects for more details. Unit testing and continuous integration is an extremely standard technique throughout the software industry. There's very few segments or none really that don't use it. Modeling code is an exception, and it should not be. We need to use these techniques because they're very, very effective. Let's just define what we're talking about here. Unit testing is when you're testing the subroutines and the functions with test programs. So to put it in a modeling example, you have a large number of Fortran functions and subroutines, and you write a test program for each of them, or multiple test programs for them, which run them with controlled inputs and look at the outputs and make sure they did it correctly. That's a unit test. When you write your unit test as you're developing your code, we call that test-driven development. It's been proven to be extremely cost-effective. And when you run all your tests every time your code changes, we call that continuous integration. Okay? As I said, these techniques are ubiquitous in industry, and the benefits they deliver have been proven time and time again. A unit test is a program that exercises your code. It can be in any language. It's distributed with the code. It can be built and run by the users when they build your code. When they build your code, then they get to run all the tests, and then they have confidence that their build worked and your code is now working on their platform. When you have a unit test, you need to return a 0 for success and any other value for failure. So how does that work? Here's a C example. This is, I believe, from the Parallel IO project. And there's an error macro, which is defined in the code, and then it's used as shown here at the bottom of the screen. When there's an error, the error macro is called and it returns the error code to the operating system. Similarly, in Fortran, we can do the same thing with a stop. So here I'm saying stop 2. So every error code is 2 for this program, but it doesn't matter because it's not 0, and that's the important thing. What you need to realize is that no one has to look at the output for this to fail or pass. There's no human involvement. When testing science codes, you frequently need some kind of test data to start with. And how do you handle that? If it's text files or small configuration files, you can include them in the repository with the code. For example, NetCDF does this with NCDump, which is a very commonly used utility to dump NetCDF files into text format. And tests consist of a bunch of outputs for different files. And those outputs are kept in the repository. And when the tests are run, then they're compared. Sometimes when you have a very small data file, you can include that in the repository. I would not put more than 50 megabytes total in a repository. I think even that's a lot. Large data files can be fetched from an FTP site. So we do this with the NOAA tests. We have a lot of large data files, many megabytes, and we need them for the test. So we have the test fetch them from a public FTP site where we've stashed them. GitHub also offers the so-called large file service, which essentially does the same thing. However, it costs money, and this was free. The best case solution is to construct your test data files with your test code. So have your code start by constructing a data file and then have other code read the data file and do something to it. That way you don't have to move around data files. Another problem with science codes, with all the example codes and many others, is you often have parallel codes, parallel I/O codes that use MPI. And how do you run those? When you're using either AutoTools or CMake, you can use a kind of a run test script, which you build, and it runs it using MPI. With the Parallel I/O project, we have some special CMake functions, which allow you to run tests with MPI exec. And on the GitHub nodes, of course, you have to use a small number of processors. You can put in any number that you want with oversubscribing, but if you use more than 4 or 6, it's going to be tremendously slow. So with Parallel I/O, I use up to 4 processors to test for most of the tests. NetCDF uses 4 for most tests, but in a couple of tests, I use 16 just to make sure that those work as well. But when I'm writing a test that's going to use 16, I make sure that that test is a very light test. I don't do anything crazy because using 16 cores on a GitHub machine would be pretty slow. MPI can be installed by the package management system, and I'll show that in a little bit, or you can build it as a dependent library. Okay, so how do you use all this wonderful stuff? It's very easy to get started. Excuse me. There's on your repository, there's an Actions tab, and if you click on it, you get this lovely screen, get started with GitHub Actions, and you click this button here, and you will get a base action with some stuff in it. Now I'm going to explain what's in these files. Your actions, the build is controlled by a YAML file, which also lives in the repository in a special place. And that special place is .github workflows. And you can put as many in there as you like. And each time you do, it will be run as a test. And I'm going to explain it kind of line by line here. But that's the start of it, and that's the end of it. This is a full example from the Parallel I/O project. And let's take it a piece at a time. So at the very top up here, we have just the name of the, oops, there we go. We have the name of the workflow, which is used in GitHub output. And here's an example. This is the top one. It's called AutoTools_Ubuntu_latest. And later I started using the version numbers of the various dependent packages and the names to help me keep track of what's being run in each test. You specify here in this section the branches that you're going to be testing, in this case master, and we're testing in particular pull requests that are applied to master. That's what you really want to do. We can specify Mac OS, Ubuntu, or Windows. This test is done on Ubuntu. We have other tests on NCEP libs that are done with Mac OS, and Windows is available. I don't use Windows tests myself. The distribution changes from time to time, like Ubuntu latest gets updated, and that can cause your test to break. This just happened to us. So you have to just keep an eye on it and keep everything updated with the latest Ubuntu. And when you're doing all this, what happens is, of course, GitHub is spinning up a virtual machine and running everything on it. Okay, so the next section here, you can set environment variables for your build. Here I'm setting MPI CC and MPI Fort so that we're going to do a parallel IO build here. Note that I'm using home runner here, which is a Unix convention. If this was then run on a Mac OS, that would break because Mac OS uses users, not home. So there's the home environment variable that I should be using there, but I'm not. In this step here, we check out our repository. So this workflow is part of parallel IO. So what will happen here is the parallel IO master branch will be checked out by that step. And in this final step on this screen, whoops, I'm sorry about that. We're using apt-get to install a bunch of packages that we need. For example, netcdf, Doxygen, Fortran. These are all being installed on the virtual machine right there. Moving on to the next screen. Okay, so one thing you want to do, sometimes you want to use a library that's not included in any of the repositories, any of the package management systems that you might use. Or you might want to use a newer version of a package that's included in the package management system. So here we're using a library called pnetcdf, and it's not in the package management system as far as I know. So I must build it each time I want to run the tests. Now that is a slow process in general, and so we use something called GitHub caching. And this section of code here that's highlighted in black at the top of the screen sets up a cache for the built pnetcdf library. And there's a couple of important fields in there. The path field says what is going to be grabbed and cached. So you're going to install everything in this directory, and I'm going to grab it and cache it. The key is very important because if you change the key, it will refresh the cache. Okay, so the key is how it keeps track of what's been built. And here we build the pnetcdf library. This line here ensures that this only happens if the cache is not available. So the first time this workflow is run, pnetcdf cache will not exist, and it will build it, and then after that, it will not build it. And here we build it in a very standard way, as you would from the command line. Finally, after all of that, we're all set up, and we run auto reconf, configure, and make check to test our repository. So this is doing our code. Okay, so once we've done that, what happens? Here's a screen of pull requests from the UFS Utils project at NOAA, and it is showing a bunch of pull requests, many of which have failed and 2 of which have passed. And you can see the ones that have passed have a green check mark, and the ones that have failed testing have a red X. If you open up one of the pull requests, if it's a successful one, it will look like this. And you'll see, wow, no, nice green. Everything looks lovely. And if you open up one of the failed ones, you'll see this. So it's very clear. And because of the way we've configured GitHub, it will not let us merge if the checks have failed. So you cannot accidentally merge broken code. If the code doesn't work, it cannot be merged. When you want to look, the output is there. This is a screen showing the output of one of the successful runs. I will say that debugging problems on the GitHub Actions platform is somewhat laborious. It's slower than the computer I have right in front of me, and I don't have as much access to the outputs. I can see everything that goes to standard error and standard out, but I don't have the output files that I could look at. So when I do have an error or a problem, I tend to try and first reproduce it on my local system, debug it there, and fix it there rather than use GitHub for debugging. So one special thing that we do with this, which is fun, is we use this to run test code coverage to tell us which of our code is being tested and which isn't. I saw a presentation, I believe a couple of days ago, in which the presenter mentioned CodeCov, which is a service you can pay for, but this method is completely free. So this is an example from the UFS Utils project under NCEP libs. And down here at the bottom, you can see there's a gcovr command line, which outputs the test coverage. And then there's this extra upload artifact section. And the end result of that is that when we run this, we have this over here, a little button that says artifacts. And when we click on it, we can download the HTML files, which give us this report. And here on this side, we see our code files listed and the percent coverage. This is a project that has no testing yet, or very little. So you can see we're doing quite poorly there. And then when you click on the files, you can actually go down and see which part of your code is being tested and which part of your code is not being tested. Right, so you can write targeted tests to make sure you're testing all your code. I think I've ran through my presentation a little more quickly than I thought here, but I have some pointers to the science code examples that I used for this presentation. The Parallel IO library demonstrates building and caching a bunch of dependent libraries, including the MPICH library, the OpenMPI library. It contains the CMake code, which allows you to run parallel IO tests easily. And this project, because we wanted to test with the latest MPICH release, we could not use the one from the package management system. So we have a build which downloads MPICH and builds it from source and then caches the result. So this demonstrates how you can use GitHub Actions to test against tools, even if those tools have not made it into package management systems yet. Another thing we do on the NCEP libs project is we can check Doxygen completeness. So we're using Doxygen for our projects, and when you have Doxygen in all of your code, you can turn on Doxygen warnings, and then you can turn on a little flag warn as error, and then your build will fail if someone is trying to submit code that is not properly documented. Now you still have to go inspect the documentation because they could have just entered nonsense, but Doxygen can check that they have entered documentation for every parameter and function, etc. The NCEP lib projects is also where we do that example I just showed, where we measure the code coverage so you can see what your tests are covering. The CCR project uses the GNU address sanitizer. So the GNU compilers come with a feature called address sanitizer, which you can turn on with a couple of compile flags. It works with Fortran and C and all GNU compilers. And it will keep track of memory internally for you and tell you if you have left any memory unfreed or if you are doing anything illegal with memory. So it's extremely useful to run on your code. What you do is you turn the flags on and you run all of your tests, and you have a pretty good confidence then that you don't have any memory problems in your code. So similar to what I just explained with the Doxygen, you can set this up so that if the address sanitizer fails, then the continuous integration step will fail. And that way no one will be able to check in any code which contains memory bugs. Also in the CCR project, we build and cache a bunch of dependent libraries, and we demonstrate how to run parallel code with shell scripts in testing. And this is my last slide, so I'm quite a bit early. I would like to acknowledge my collaborator, Kyle, at NOAA. I would also like to mention that the parallel I/O testing is maintained with my colleague Jim Edwards, who works at NCAR, and the CCR testing is maintained with Charlie Zender from UC Irvine. Thank you. Does anyone have any questions?